I'd like to talk about graphing exponential functions. Here's an example of an exponential function. It's y equals a constant raised to a power, and that variable is in the exponent. So y equals 2 to the x power is an example of an exponential function. So let's graph it, and I have this set up for us to plot points. As you know, that's a common practice when you don't know what the graph is going to look like as a starting place. After we know what exponential functions look like, then we won't be needing to plot points every time we're graphing. So I put in some values. So let's put in an x value of 3. So we have 2 to the third power. We know that's 8. We'll put in 2 for x, so 2 to the second power is 4. And you'll notice we'll have powers of 2 working down in the y column. We put in a 1, 2 to the first power is just 2. And put in 0, remember 2 to the 0 power is equal 1. Any constant except 0 raised to the 0 power gives us 1. Let's put in negative 1. We have 2 to the negative 1. Let me remind you what that looks like. 2 to the negative 1 means we have 1 over, remember negative exponents, 1 over 2 to the first power, which is just 1/2. Similarly, when we substitute in negative 2, we would get 1/4. And we substitute in negative 3, we have 1/8. So notice again our powers of 2 along this column. Now I put in a different x value because I wanted to be clear that we don't just put in integer values for x. X can be any real number, so I just decided we'd throw in 1.5. So I'm grabbing my calculator and I raise 2 to the 1.5 power, and we get about 2.8. So I'll even put that on the graph when I go to graph y equals 2 to the x. So let's plot these points. We have 3, 8, so about right here. 2, 4, 1, 2, 0, 1, negative 1, 1/2, negative 2, 1/4. Oh, it's getting smaller, harder to see here. Negative 3, 1/8. You can't tell, but it's because it's so close to the x-axis, right? You can't really distinguish too well on my graph that this is 1/4 and this is 1/8. But notice it's getting ever closer to the x-axis. And right here, let's even pop in this 1.5, 2.8. So 1.5, 2.8 is about right here. And we'll make a smooth curve through these points, or as smooth as I can make it. And we see we have a graph that looks something like this. And over here, it's coming down toward the x-axis, but notice it will never cross this x-axis, because even if we put a very small number in, like negative 100, 2 to the negative 100 is still a positive value. It's very, very small. It's close to 0, but it's still positive. So this will never actually cross the x-axis. In fact, it's asymptotic there. Remember that word? This is an asymptote right here. The graph is going to approach this line. And we have our graph for y equals 2 to the x. Notice also that the y-intercept is a 1 and there is no x-intercept. Let's graph another exponential function. Let's let it be this one. Y equals 3 to the x. So I have just changed the base. The base is still a constant. Our variable is in the exponent, and that means we have an exponential function. So let's plot some points. We put in 3. 3 to the third is 27. 3 to the second is 9. And notice now we will have powers of 3 here. 3 to the first power is 3. 3 to the 0 power is 1. Oh, just like with the previous problem, we have the ordered pair 0, 1. Now when I put in a -1, I get 1/3. And then -2 gives us 1/9, and then 1/27. So let's plot these points. So 3/27 is up here somewhere. And then we have 2, 9. And then I have 1, 3. And I have 0, 1. I didn't put 1 on here, but it's about 1/3 of the way to 3. There's my 1. At -1, I'm at 1/3. Boy, it's hard to even show that. They'd start to get ever closer to the x-axis. It's just going to look like it's lying on the x-axis. But as with the previous example, it will actually never touch the x-axis. So our graph looks like this. Let me draw a smooth curve through these points. Again, the y-intercept is 1. Again, we have an asymptote right here. And we have our graph for y equals 3 to the x. Let's do one more. Let's let it be y equals 5 to the x. So again, I've just changed the base and I still have my exponential function. Let's see, we could put in the value 3 as we did on the previous one. We will get 5 cubed, that's 125. I didn't even make it go that high, but we'll talk about that in a minute. If I pop in 2, I have 5 squared. I put in 1, I have 5 to the first power. Now I'm talking about powers of 5 here. We substitute in 0, we get 5 to the 0. Oh, and there's that ordered pair 0, 1 again. I can put in -1, and I have 5 to the -1 power again. That means we have 1/5 to the first power, or just 1/5. Similarly, -2 will give us 1/25. And maybe that's enough for us to get a good look at what the graph looks like. I'm going to start with 0, 1 this time. I'll put that point in. 1 looks like it's about right there. Now I have 1, 5, 2, 25. Now 3 is a 125, very high. This one is steeper than the previous ones. At 3, we're all the way up at 125. So same general shape, but it's a little bit steeper. And here at -1, it's all the way down at 1/5. At -2, it's at 1/25. It is approaching this x-axis very quickly. So we can hardly distinguish the graph from the x-axis itself with this particular scale. And again, we have an asymptote right here. And I hope you recognize how similar the graphs look. Let me bring the other two back in. This is y equals 5 to the x. This was y equals 3 to the x. And this was y equals 2 to the x. They all had that same look. Now let me show you how the 3 compare on the same set of axes. I put them all on the same set of axes here. And you can compare. Do you see that they have that same general shape? They all went through the point 0, 1. That was the y-intercept. But the 5 to the x was steeper. The 2 to the x wasn't quite as steep. 3 to the x was steeper. 5 to the x is steeper. And if we were to increase the base, they would become steeper still. Anytime you have y equals b to the x, where the base is a constant greater than 1, you're going to have this kind of a look. The larger the base, the more sharply it will head toward those large values. Notice the domain is from negative infinity to infinity, but the range is from 0 to infinity. The graphs will never cross the x-axis. You can't tell it very well, but the larger the base, the more quickly the graph approaches this x-axis. The 5 to the x graph was hugging the x-axis much more quickly than the y equals 2 to the x did. So this is what I want you to keep in mind. Y equals b to the x will have this kind of a look, and it will, we could make the base be anything greater than 1, and we can know that the graph looks like this. What if the base weren't bigger than 1? Suppose we had something like this, where the base were a half. Let's plot some points here. Let's put 3 in, for example. If we put 3 in, we have 1/2 to the 3rd power, which we know is 1/8. Similarly, if you put in 2, you'll get a quarter. 1 will give us a half. 0 will give us 1. And there's that point again. -1. Now let's see what we get when we put in -1. Remember, 1/2 to the -1 means we're going to take the reciprocal of the base because of that negative exponent, becomes 2 to the 1st power, or just 2. Similarly, we put in -2 and we'll get 4, and -3 gives us 8. And again, we have powers of 2, or powers of a half. So 3 is 1/8. 2 is 1/4. Again, hugging the x-axis. 1 is 1/2. 0 gives us 1. -1, we're at 2. -2 is at 4. -3, and we're at 8. And notice we have the same kind of shape that we had before, except from left to right. Let me finish drawing it. From left to right, this graph is decreasing instead of increasing. It's coming down from left to right instead of going up. It turns out anytime your base is between 0 and 1, the graph will take on this look. So let's put this, and also notice that our x-axis is our asymptote again. So let's generalize what our exponential functions look like. Here we have it. If you have y equals b to the x, and b is a constant, and b is greater than 1, we have an increasing exponential function. Notice it goes through 1. If you have y equals b to the x, and b is a number between 0 and 1, we have a decreasing function. In both cases, this x-axis is playing the role of an asymptote. So what we know is that every function can be transformed in the same way. We've done transformations before on how you can manipulate graphs if you know the transformation and you know the base graph or the parent graph. So let me show you what I mean. Let's move on. Let's do some sketches of some exponential functions. Let's graph y equals 3 to the x plus 4. Let's just start by thinking about y equals 3, or f of x equals 3 to the x. You know it doesn't matter if it says f of x or y. We look at that and recognize the base is bigger than 1. So I'm thinking, this is my scratch work, I'm thinking, okay, I have an exponential that is increasing. So this is what I'm thinking. This isn't my answer to that question. I'm thinking, there's my exponential with my asymptote here. As always, when you add a constant to a function, you have a vertical shift up or down. we're adding a positive number, so we're going to shift the graph up 4, as we've done with other functions. So here's going to be my graph. Y equals 3 to the x plus 4. Here's my base graph. I'm shifting it up 4. If I had an asymptote at 0, my asymptote is now going to be at 4. 1, 2, 3, 4. I'm going to label that and draw in my asymptote. That's an important detail. And instead of having a y-intercept at 1, it gets shifted up 4 as well. So instead of being at 1, we go up 4. 1, 2, 3, 4. And we're here at 5. If you can't remember for certain where it would cross that y-axis, just substitute 0. And nothing wrong with plotting a point. Put in 0 and you'd have 3 to the 0 is 1. 1 plus 4 is 5. And we recognize that we have a y-intercept at 5. I know that's my general shape, and I'm going to draw this sketch. Now you'll notice I didn't plot any points. It depends on what level of detail is required. Sometimes you need a quick sketch, and I mean like a 10 or 15 second sketch, and this is good enough. And because you might need to go on and do something else for the problem, and you could present this as the answer. And you might be thinking, but you didn't even use the base of 3. Well, I used the base of 3 knowing that it was increasing, but I didn't really distinguish whether it was a base of 3 or a base of 4 or a base of 2. I just did a quick sketch. If you were needing a little bit more detail, then maybe you could plot a point like 1. Pop 1 in, and you'll find that at 1, 3 to the first power plus 4 is 7. So maybe it's a tad bit steeper, and you could refine your graph and realize, oh, okay, it should be maybe here instead. But often, just a quick sketch is enough. It depends on the point of coming up with your graph. Let's do this next one. And of course, we don't have both of these. We'll just leave it this way right here. Y equals 6 to the x. Again, we have a base. Remember, this exponent does not apply to that negative sign. We don't have parentheses. So this is our 6 to the x graph. So again, I'm thinking about the general shape being an increasing exponential, looking like that. Remember, a negative in front of the function means it's reflected across the x-axis. So instead of being up here, when we reflect it, it's going to be down here. So let's draw that. We reflect across the x-axis. Instead of being at 0, 1, we're down at 0, negative 1. Let me put that point in. And now I could just draw the shape. Let me draw it here in pencil for a minute. I'm thinking, okay, this is what my graph looks like. I've reflected it across the x-axis. Again, depending on what level of detail you need, that might be good enough. If it needed to be a little more accurate, let's plot a point. Let's put in 1, for example. And if you put in 1 into the function, the opposite of 6 to the first power is negative 6. Maybe we would put the point down here. Oh, maybe I should make it a little bit steeper because my base is a 6, not a 2 or a 3. So I'm going to refine my graph and make it look more like this. And here was my negative 6. And because the base is a 6, it comes up and hugs that x-axis a little bit quicker than, say, 2 to the x. And I will erase the little rough sketch that I had right here. But I have my exponential function graphed. My base graph reflected across the x-axis. Let's do another one. Y equals 2 to the negative x. Maybe you remember that a negative in front of the x reflects the function across the y-axis. But what if you don't remember that? Let's think about this graph another way, or this function another way. A negative exponent, remember, always means we can take the reciprocal of the base and rewrite it with a positive exponent. So that g of x could be written as 1/2 to just the x power. And now we know this is a decreasing function. Remember, if the base is between 0 and 1, we have a graph, and this is actually the official answer to this one. I could have done it a little bigger. Goes through 1 and it is decreasing. There's an asymptote right there, and it's heading up in this direction. So from left to right, it is a decreasing function. And again, as a 10 or 15 second sketch, done. If you needed a little bit more, plot a point, put in -1 and find a value, +1 and find a value, maybe 1 point on either side of 0. But this is a pretty good rough sketch of that particular function. Let's do our next one. F of x equals e to the x plus 2. E, remember, e is a constant in the same way pi is. It's our irrational number that is about 2.7. So remember, this is now a base between or greater than 1. E is approximately 2.7. Remember, it was the 2.7182818, and on it went. But if with a base that is bigger than 1, we know that our exponential function looks like this, our increasing function. And now notice we have an x plus 2. Remember, when 2 is added to the x when you're dealing with a function, that means we shift it left 2. So I'm thinking about this base graph being shifted left 2. Let's do it. Here's a key point. This point that was at 0, 1, let's pick this graph up and move it over 2 places to the left. -1, -2. So instead of being at 0, 1, this point will be at -2, 1. Right here. And now my graph will be increasing, but with this key point right here. I know it's going up this direction. Notice I'm sketching it here in pencil because I might want it to be a little nicer. Maybe I would have a nice y-intercept so it looks even better. But a rough sketch, it's done with this clearly labeled right here. So anybody looking at it can tell this is an exponential function that has been shifted left 2 units. Notice if you substitute in -2 into the function, you would have -2 plus 2, that is 0. And here's what I'm saying. We're putting in -2. -2 plus 2 is 0. E to the 0 power is 1. And here's how we get that point. Now suppose I want this y-intercept to be very accurate. I know if I put a 0 in, I have e squared. Let's put that into our calculator and see what it is. E to the 2nd power. So e to the 2nd power is about 7.4. 7.4. So if this is 1, maybe I need to make it a little bit higher. 7.4 maybe is up here. So a little bit steeper, but not bad. Notice I'm not going to adjust my graph very much to try to get it to cross right here at e squared, or at 7.4. I didn't have it very curved, and it comes down towards the asymptote. I'd like to make it a little more curved right here. That's a nice thing about using pencil. You can edit it a little bit better than I can with this marker. But here's my exponential function. Again, this key point right here, very clearly labeled at -2, 1, so anybody looking at it can tell it was shifted left 2 units. Let's graph one final one. Let's graph y equals 3 times 2 to the x. Again, our base graph looks like this. Our 2 to the x graph looks like this. Remember what multiplying by 3 does to a function? It stretches it out with respect to the x-axis. So let me do this. I'm going to graph y equals 2 to the x for just a moment here, and I'll do it in pencil. Here will be, let me make it a little bit lower. Here will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We'll stop here at 12. So I'm ignoring the 3 for a moment, and I'm just giving myself a nice little sketch here. I'm going to make it pretty accurate here. 2, 4, and then 3, 8, 4, 5, 6, 7, 8 right here. So I have y equals 2 to the x. That looks something like this. Now when we multiply by 3, remember all the graph is stretched out by a magnitude of 3. So all of our old y values are multiplied by 3. So instead of having an intercept at 1, I would have it at 3. Instead of being at 1, 2, it will be at 1, 6. This is 1, 2, 3, 4, 5, 6. So instead of 1, 2, I'll be at 1, 6. And notice if you substitute 1 in, you can confirm. This point right here that was at 4 will be multiplied by 3. It will be up here at 12. This point that is here at 8 will be at 24. So it will be looking like this. But I want to point out that it will still be asymptotic to this x-axis, because when we're at a half, multiply a half by 3, you're at 1.5. But if you come way down here and you're at, say, 1/16, if you multiply 1/16 by 3, you're still at 3/16. You have 1 over 64, you're at 3/64. When you have very tiny, tiny numbers over here and you multiply a tiny number by 3, it's still a very tiny number. So we will still have an asymptote there. So here is our graph. Let's get rid of our 2 to the x graph that I did initially. And here's our y equals, let's make it look nice here. Here's our y equals 3 times 2 to the x. Y-intercept 3, still asymptotic to the x-axis. I hope you'll go graph some exponential functions.